Real quick with function transformations, we're going to practice combining the transformations with parent functions. So we've talked about all the parent functions so far. We've talked about transformations. You can apply the transformation rules to parent functions. So for something like question 1, first off, how do I know from this right here what the parent function would be?
Absolute value.
Absolute value. We see that in the formula. Okay? So my parent function that I'm working with is y equals the absolute value of x. In order to do transformations, we usually like to have tables of values. If you do not have tables of values for parent functions memorized, it is not a problem. Most of us know how to plug in numbers, right? Make it easy on yourself. If I was to find some points for the absolute value parent function, what x's could I plug in? Let's just pick 3 x's to plug in. What are some good ones to plug in? 1. What else?
2.
Okay. I would probably try to plug some in the middle. Like, what does the absolute value parent function look like, if you remember that one?
Oh, yeah.
It's that V-shaped one, right? So what's right in the middle?
0.
0. Then I would plug in 1 number to either side, typically, just to make life easy. And these are the easiest ones to plug in.
So you're plugging in x.
You're plugging in x. So if I did the absolute value of -1, it makes what? 1. If I did the absolute value of 0.
0.
And if I did the absolute value of 1?
1.
1. Okay, so those are my 3 parent function points I'm going to start with. Then we're going to do the transformations to those. So if we go back and look at the original one, I'm not going to have you fill out A, B through L here. You're just going to write down your transformations. What does a -2 inside with the x do to your function? It moves it right 2. And what does that do to your table of values? Adds 2 to the x's. So I go through each of my x's and I add 2 to each of those. What's the second transformation that I have here? Up 4. And what do I do to my table of values to get that? Add 4 to my y's. And then I graph my points. And that's it. 1, 5, 2, 4, 3, 5. You still have to know what the parent function looks like. Like, you know the absolute value is that V-shaped graph, so you can connect your dots going out this way and that way. Okay. Any issues with that? All right, 2. What's our parent function in 2? It's a cubic. Y equals x cubed. Again, if you don't know what that graph, like what the points are on that graph, that part you probably will have to memorize, yes. What numbers could I plug into my cubic graph to get numbers back out? I can still do -1, 0, and 1. It does help if you kind of know what the cubic looks like when you're doing this, because you'll see when you get your points back out, you can connect them in a lot of ways. If I cube -1, what do I get?
1.
-1.
Oh, -1.
If I cube 0
0.
and cube 1, 1. Now, don't graph this over here because we're using this graph for our transformations. But if I graphed those 3 points, it looks like that. If you don't know what the cubic looks like, that's not going to help you a whole lot. You could do what if you didn't know what your cubic looks like? Plug in more points, right? If you don't know, just keep plugging in numbers on either side. Go to -2 and +2 and see what you get. But here's where, if you know your parent functions, it does help you, because what would that look like?
Wait, so how do you know what your y is?
You would cube that to get your y. It's like that S-shaped graph.
3 minus 2, right?
No, we're not going to do that yet. We'll do that in just a minute for the
'cause we're just
transformations.
doing the parent
We're just
function
doing the
right
parent
now.
function. Yep. If you remember, you don't have to plug in more, and you can just remember that it's this S-shaped looking graph for your cubic. If you don't remember, keep plugging in numbers. -2 cubed gives me -8. +2 cubed gives me +8. So then you could see what it looks like after that. But again, having that mental idea of what it looks like, that's just part of knowing our parent functions. Now we can do our transformations to these. So this one has quite a few transformations to work with. The -3 out front, that's actually 2 transformations. What's one of them? It's a vertical stretch of 3 because of the 3. What does the negative do? It's a reflection. What is it reflecting it over? X-axis. Good. Now we also have a -1 inside. What does a -1 inside do? Right 1. And what's the +2 at the end do? Up 2. So now if I was to do all of those transformations to my table that I have here, what do I have to do first? Hang on. Okay. I have to first multiply my y's by -3. That does the reflection and the vertical stretch at the same time. Now these, can I actually graph these? No. Some of them I can. The 8s, that doesn't really help me on this case.
But why can't you just keep your x's and then like figure out your y's from your x's and then your x's alone?
For the transformations or for the apparent functions?
Like, why can't you just plug numbers in?
You can.
The equation.
It doesn't help you know the transformations.
You already know the transformations.
Like the right 1 up to reflection.
Yeah.
That doesn't, if you're just plugging in numbers to the function, it doesn't help you know the transformations. If you know those, you're welcome to do that. I think mathematically, to me, that's a little bit harder to do that because you're going to end up like cubing some big numbers and you don't always know what numbers to plug in because you don't know where the central part of the graph is without thinking about the transformations.
So if I plugged in -1 to that equation, I would get the y we're about to make. Right?
Yeah. Yeah, you would. It's just helpful when it comes to like finding the middle part of the graph. I start with the middle parts of the parent function so that when it transforms, I still have the middle part of the transformed function. If you're always plugging in easy numbers to that, you're not always going to have the middle part of the graph, and you could just have a weird section of it. That's the only problem with it. So after we multiply this one by -3, we have to do 2 more things to it. What are the other things we have to do? Okay, to move it right 1, what do we have to do? Add 1 to what?
The x.
The x's. So I add 1 to my x's. And what do I have to do to my y's to do my final points?
Add 2.
Add 2 because of the up 2. I'm only going to graph the middle 3 here because the other ones won't fit, clearly. So these 3 points, when I graph them, 0, 5, 1, 2, and 2, -1. Again, if you don't have an idea of what your cubic looks like, it makes it very hard to connect because that looks like it's in a straight line, but remember it's always that S-shaped curve, like that. It's just stretched it out and made it really skinny. You can tell because of that 26 and -22. That general idea. More of what I care about than the graphing is knowing the transformations and knowing how to do the points. The graphing is less important. Okay. Let's do one more of these together, and then I'm going to let you do a couple at your table so we get practice with this. Question 3 at the bottom, what's the parent function? Square root. All right, again, if you don't know the square root points, what can we do? We can just plug in numbers. So my first question would be, can I plug in negative numbers to a square root? No. So where should I start plugging in numbers? 0. And if you were being nice to yourself, I might not just plug in 0, 1, and 2 because I would be thinking, can I square root all of those nicely? No. So I would say, all right, I can square root 0. That gives me 0. I can square root 1. What does that give me? 1. What's the next number I can square root? 4. That gives me 2. So I might just start with those. And if you don't remember, you can draw yourself a little sketch. This is your square root function going out to the right. Okay? Then we'll do the transformations to that to get our new function. So here is what we were just talking about. If there's a negative inside in front of the x, what does that mean? A reflection over the y-axis. Yes. Right, because of the square root. It's inside the function because it's inside the square root. Then the -1 inside the square root means what? right 1. And the plus 4 outside means up 4. Okay, so what operation do I have to do to my table first on this? Multiply the negative ones by the x's, right? Then I need to move it right 1, which is going to do what to my x's? Add 1. And that is then going to move up 4, which means what am I going to do to my y's? Add 4 to each of them. So when I graph my points, it's now reversed. So 1, 4, 0, 5, negative 3, 6. It has flipped over the y-axis, which means it goes the opposite way. It's moved right 4 and up 1. Okay? So what I would like for you to do at your tables to practice 4, 7, 8, and 10. 197 is where we're at for this. Inverse functions, the main thing you need to know, this switches x and y completely. If you want to find a function's inverse, you switch the x and the y, and I mean that literally with the algebra in it, which is what we're going to do on the next page, and it also means on the graph, okay? An inverse function always reflects over the line y equals x. So just a quick do one where you see this visually here. What are the 4 points that we have on this original function here?
Negative 7, 6.
Negative 7, 6. Negative 2, negative 6. We have the point 3, 3. And we have the point 8, negative 9. So even though I don't have an equation for this graph, if I wanted to find its inverse, the easiest way is to literally take your x's and y's and flip them. So that first point, instead of being negative 7, 6, it's going to be 6, negative 7. That second point becomes negative 6, negative 2. Third one, what happens when I switch the third one? It's the same because the x and y are the same. And then when I flip the last one, it becomes negative 9, 8. So you can graph the inverse of this by graphing those points. So 6, negative 7 was my first point. Negative 6, negative 2 was my second. I'm going to connect those while I go because otherwise I'm going to forget which ones connect to which. The third point is 3, 3. That one doesn't switch because it's on the line itself.
Wait, how do you know which ones they connect to?
I'm just going in order, first, second, third, fourth. That's the easiest way to do it on one of these graphs. And then negative 9 up 8 is your first or your fourth point, which is your last one. It would be very difficult to see the reflection over the line y equals x, so the easiest way to do it is to just switch your x and y. That's it. That's if you're given a graph and you don't have an equation for it. You can always just switch the x and y points. That will give you the inverse. Mostly we're going to be doing this with algebra, which is on page 199. So flip to page 199 real quick. We'll do 2 or 3 examples of this and I'll be done. The main reason we talk about these things is so that we can do them using a y equals equation. There are 3 steps to finding an inverse here. They are right here. If you are given an f of x equation, you replace your f of x with y. Again, I told you with inverses, everything is about switching your x and y. So that's your step 2, switch your x and y. Step 3 is solve for y. Okay? So first we're just going to graph this function. This is a line. How do I graph a line? Start at where? Negative 3. So I start at my y-intercept of negative 3. Then I go which way?
Up 7, left 2.
I can go up 7, left 2.
Or down 7, right 2.
Or down 7, right 2. Either way, that gives me my original line. What domain and range is this line going to have? Negative infinity to positive infinity. Both of them. Lines are always that way. Now, if I want to find the inverse of this, which first off, How do I know it wants me to find the inverse? This notation right here. That looks like f to the negative 1 of x. This means the inverse. So to find the inverse of that function, I'm going to follow these 3 steps up here. I'm first going to replace my f of x with y. Step 2 is what? Switch your x and y, and that literally means y becomes x, x becomes y. You don't take anything else with it, you just switch them. That's it. Then I must solve this for y in order to get my new function. So how do I get y by itself? Add 3. Now, for those of us that don't like multiplying by the reciprocals of fractions, what else could I do? How do I get rid of divided by 2? Multiply by 2. So you could do this in 2 steps if you wanted to.
Can you not just plug the numbers in?
Plug what numbers in?
Like, once you switch them?
I'm not 100% sure what you're saying.
Like, can't you just plot the points that you have on the regular
You can, but it's not going to give you the equation.
Oh, and we need the equation.
We need the equation. Yep. So then my last step here to get my equation, if you don't like multiplying by fractions, this is 2 parts. I would solve by doing what? Divide everything by negative 7. Okay, so when I do that, my inverse equation is going to be y equals what? Okay, negative 2/7 x minus what's going to be my y-intercept? 6/7. Not a super nice line to graph, right? Because it would have a y-intercept of what? Negative 6/7, and I would have to count down 2/7 from that fraction. If I don't feel like graphing that line, what's the other way I can graph my inverse?
Multiply by 7. Or no.
I can take my original points from my first line and do what with them? Switch them. So for example, this point right here, what is that point?
Negative 2.
Negative 2, 4. If I flip it, make the x the y, I can make that 4, negative 2. That's going to be on my new line. Second point, this is the point 0, negative 3. If I flip it, it becomes what?
Negative 3.
Negative 3, 0. Third point is the point 2, negative 10. If I flip it, it becomes
Negative 10, 2.
negative 10, 2. And when I connect my dots, I would check, does this look like a line with a slope of negative 2/7 and a y-intercept of negative 6/7?
Yes.
It does, and I didn't have to graph that ugly line, okay? Notice these should be reflections over the line y equals x for us. If I drew that in there, that should be flipped over that from each other. And then the last thing that flips for us, remember we were saying with inverses, all x's and y's flip. The other way we represent our x's and y's in these are our domain and range. Domain is what? X, and range is? Now in this case it doesn't matter because they're the same, right? But it will help you in the future if you remember from your original equation, your domain becomes your inverse's range. And your range becomes your inverse's domain. It switches. This one, like I said, it doesn't matter, but the next one we talk about it will. Okay. Any questions on finding the inverse?
Wait, so the black line has to go through the middle of those 2 points?
It should, yes. If you've graphed it right. All right, flip to the next page. Let's talk about how to find an inverse of a square root function, and then we'll do one more together and be done. All right, if I wanted to graph that square root function, this reviews our transformations again. I know it's a square root function, so the parent function is the square root of x. What points did we plug in to find the parent functions when we did this on transformations?
Negative 1, 0, 1.
Okay, this one we couldn't square root negative 1, so where do we start? 0. Square root of 0 is? 0. Square root of 1 is? 1. What's the number next number I can square root? 4. Gave me? 2. And then what was the transformation done in here? That means what?
Left.
Left 3, which means I subtract 3 from each of my x's.
Why didn't we do that?
Because we knew how to graph the line without doing it. Yeah. This one, I'm using this as an example, like if you don't know how to graph that without a calculator, you can use your parent functions and transformations. So this graph originally looks like negative 3, 0, negative 2, 1, and positive 1, 2. Here's my square root graph. What is the domain of that graph?
Negative 3 infinity.
Negative 3 out to infinity. Good. What is the range?
0 to infinity.
0 to infinity. Good. This will matter when we switch my x's and y's and find my inverse. So algebraically speaking now, to find my inverse, I write my equation as y equals the square root of x plus 3. What's step 2 in finding my inverse equation?
Switch them.
Switch my x's and y's. That becomes x equals square root of y plus 3. Step 3 is solve for y. How do I get y by itself?
Subtract 3.
Before I can do that, I have to
Square it.
square both sides. That gives me x squared is equal to y plus 3. Then I finish out by doing what? Subtracting 3. So my inverse equation is x squared minus 3, right? Now, someone tell me the problem with this. What does an x squared graph look like?
It's like a square.
Okay, it's a quadratic, right? That starts at minus 3. So don't draw this whole thing if you're drawing in pen right now. But this is what my quadratic would look like. How is that an inverse of my green graph? It's not. What matters is my domain and range. So let's look at that quick. What did we say about your domain and range from the original? They do what for your inverse? They switch. So if I bring those down and write them, it's going to help me see this a little bit better.
How'd you find the points for the inverse?
For the inverse,
Yeah, could you just
I just knew how to graph the quadratic. That's just a quadratic move down 3. It always starts at 0, 0, and you move it down 3. If you don't know how to graph it, though, remember you can switch your x's and y's from the original points. But this is what I wanted to show you with this, because some of us get confused by this. Look at our domain here. My domain says it starts at 0 and goes out to infinity. So that's saying my x values start at 0 and go which direction, the right or the left?
Right.
Right, out to infinity. So that's saying basically to cut my quadratic right there at 0 and keep which half of it? The right half.
So can you just like draw dots
Mm-hmm.
to like signify that?
Yeah, you can draw dots for that, or you can just switch your x's and y's and switch your graph entirely. Some of us would find that a whole lot easier. Because if you take your original points here, this was the point negative 3, 0. I switch it, it becomes 0, negative 3. So if I just had switched my points, I would have only had half the graph anyway.
So whenever there is a square root function for the inverse,
It's
you're
only going to be
always gonna switch
half
the
of it.
numerator.
Mm-hmm.
And then you just like kind of like whenever you do the piecewise function.
Yep,
Just erase
you
it.
erase half of it. Or you can always remember that it's just supposed to be flipped across this line. So if you look at that, that just flips that down there. Okay? One more together and then we're done. On the next page, I want to do one that's a quadratic because it's the exact opposite of this. First off, this is a quadratic that is moved up 3. So my original function is going to look like this. And it's that U shape. So let's briefly go through this. This is my quadratic x squared plus 3. What's its domain? Negative infinity to infinity. What's its range? What's the lowest y value? 3 out to infinity. To find the inverse, one last practice with that. We write it as y equals x squared plus 3. What do I do to find my inverse? Switch my x and y. And I solve for y. What's my first step in solving for y?
You have to
Subtract 3 Then to get rid of the squared, what do I do?
Square root the whole thing.
Square root the whole thing. Now, what's the one thing we always forget when we're square rooting?
Plus or minus.
Plus or minus. In order to get the proper answer to this, you need to have a plus or minus out front of here. Now, let's think about y. What does a square root function look like on its own? It's only half of that u, right?
Right.
If I have the plus or minus, it gives me both halves, the top and bottom. Okay? So, in order to graph this, if I don't know how to graph the square root function, what's the easiest way to get the graph?
Quadratic.
Take these points and do what with them?
Flip 'em.
Flip them. This point right here is the point 0,3. If I flip it, it becomes 3, 0. This point was negative 1, 4. It becomes 4, negative 1. This point was the point 1, 4. It becomes 4, 1. And I have a sideways quadratic, which is two square root functions put together. The top half is the positive, bottom half is the negative. Is that actually a function?
No.
No, but it's still the inverse with two parts put together.
You'd have to erase.
What?
Use the vertical line test and fails.
Right. It would fail the vertical line test. For your domain then on that, what's the easiest way to get my domain? The range from the other one. 3 to 0, or 3 to infinity, excuse me. And then what's the best way to get my range for that?
Domain from the other.
Domain from the other one, they switch. Okay?
So whenever you do the square root, they switch, or whenever you do
Uh-huh.
quadratic, they switch?
Yes.
Okay.
For school, we use the following.
I'm writing your homework up on the board here.
Kenzie Arnold, Chloe Dibbler,
It's going to be numbers 3 through 7 on page, I forget my page numbers. 3 through 7 on page 205 and 206. On page 207 through 209, we are going to do questions 1 and then 3 through 7.